Welcome back. So in this video, I want to find the splitting field of the polynomial x to the fourth plus x squared plus 1 over q. So the first thing that's interesting about this polynomial is that it actually factors. So I can try writing x to the fourth plus x squared plus 1. I can try writing this as follows. And I don't really know what, A, B, C, and D are, but I can kind of deduce what they must be equal to, right? So like the first thing that I know is that B has to be equal to 1, and D has to be equal to 1, right? Because they're multiplying together to give me this constant, this 1 here. And similarly, I can figure out what A and C are. So if I look at my x squared term, if I FOILed all of this out, right? I could get x squared by taking this x squared times this 1. Or I could do this one times this one. But I could also do ax times cx, right? All of those would work. So the x squared term, if I FOIL this out, the coefficient of that is actually ac plus 2. And I can do a similar thing with the x cubed term, right? Because I can get x cubed by doing ax times x squared. Or I could also do cx times x squared, right? So the coefficient of my x cubed term is a plus c. And that's actually enough information to know what a and c are, right? Because if I look at my original polynomial, I know that the coefficient of the x squared is 1. So that tells me that ac plus 2 needs to be equal to 1. But I also have a coefficient of 0 on my x cubed term. So that tells me that a plus c is equal to 0. So using these equations, I know that c must be equal to negative a. And if I plug that in here, I get that negative c squared is equal to negative 1. And that's actually the same as c is plus or minus 1. Okay, so that's telling me that I can pick c to be plus or minus 1, and then a will just be the negative of that. Okay, so that tells me that I can factor this polynomial as x squared plus x plus 1 times x squared minus x plus 1. And then we just want to figure out what the roots of these polynomials are. So you might recognize that this one is actually the third cyclotomic polynomial. So this is phi 3 of x. And the roots of phi 3 of x are e to the 2 pi I over 3 and e to the negative 2 pi I over 3. Okay, so those are the roots of that one. And then for this one, I'm going to claim that the roots are 6 roots of unity. So one of them is e to the 2 pi I over 6, which is the same as e to the pi I over 3. And then the other one is the conjugate of that, so e to the negative pi I over 3. And you can check these. So like if you want to check that this is a root of this polynomial, for example, you can convert this to rectangular coordinates. So like this is the same as 1/2 plus root 3 over 2i. And you can check that if you plug that into this polynomial up here, you actually get 0, right? And similarly, you can check with all the other ones. So what does this tell me? Well, these 4 numbers here are the roots of the polynomial that I started with. And these are actually all powers of just this guy right here. So what that's telling me is that the splitting field is actually just q adjoin e to the pi I over 3. Or I could also, I could call e to the pi I over 3 to just be omega. And then a simpler, q adjoin omega would be a simpler representation of this. Either way. But what's an explicit way to write this, or what's the simplest way to write this? Well, again, e to the pi I over 3 is this number here, right? And everything in here is rational except for the square root of 3 in the I. So, I can write this as q adjoin 1/2 plus root 3 over 2i, but really that's equivalent to just q adjoin root 3i, right? Because this is a field extension. So if I have square root of 3i, I also have square root of 3i times 1/2, and then I also have that number plus 1/2. So, it's the same thing. Okay, so the last thing that we should probably determine is what's the degree of this extension. And for that, we just need to find the minimal polynomial of square root of 3i. So, what's that polynomial? Well, if I take square root of 3i squared, well, that's just going to be -3. And so actually, square root of 3i is a root of x squared plus 3. And this is an irreducible polynomial by Eisenstein's criterion. So that tells me that the splitting field is q adjoin square root of 3i, and it tells me that the degree of this as an extension of q is 2. And that's it.